So we have discussed equilibrium fractionation, which are the basics of fractionation. You know how the terminology works. Now I will give you an outlook of what we will do now. We will now go further, discuss how we can use this mechanism to measure temperature of reactions, at which reactions occurred. And then we will discuss a second group of fractionation reactions, which are diffuse reaction and kinetic reaction, Rayleigh fractionation. And this will give us the power to calculate evaporation and conditions at which evaporation took place. And then we will go into applications of all this. So before we go there, what we have done before the break is a calculation of fractionation. I showed you the graph, and we can do this for O18 and for deuterium at the same time. So you just do both calculations. Now, this leads us to a diagram that you see very, very often in isotope studies, which is the O18 deuterium diagram. So we basically use both values at the same time. The O18 is on the x-axis, and the deuterium is on the y-axis. Now, when we do this, so this is such a diagram, we see the deltas that we calculate from the equilibrium fractionation here, and we see the deuterium deltas that we get from the fractionation here. We both calculate them, and this should give us a straight line, or gives us a line, a relationship. And on this relationship, we should find the waters that we created at low temperatures in the lower left corner, and the waters that are created at higher temperatures in the upper right corner. And this works. So in this diagram, we have Alaska, Barrow, so we get minus 18, minus 125, 130. Cool conditions, Grimsel, Switzerland, intermediate, still quite depleted. And then Thessaloniki, minus 40, minus 8. And Namibia, minus 4, minus 20. Buenos Aires, even heavier. So this is a kind of thermometer. We can plot our water into such a diagram, and we will actually see when it's in the lower left, cold conditions, winter rain, or high in the mountains, upper right, warm conditions, lowlands. Now, we could also now check this by taking samples of water on in a basin which has different elevations. We did this in Cyprus. So we take this at, so we measure the temperature, the annual, you ask about the temperature. We take the annual average temperature at the place where we sampled, and then we plot the average isotopic composition that we have at this place. And if we do this, we actually see that this works quite nicely. So these are lines that we have calculated from Switzerland, Cyprus, where we took isotopes at different elevations, and we actually took the temperature as well at these locations. So this works. Now this is, we can use this in a way also, when you have a value, you can actually backtrack and try to calculate the temperature at which the water was created. I have prepared a graph for you doing this. So you see the O18 value calculated for a certain temperature from the alpha delta webpage, and the deuterium value, and I also plotted the temperature corresponding to that. And you see, you can actually use this from this script or from the tracer presentation, plot this inside and estimate the temperature at which the precipitation took place. Now this is a thermometer, positive values. However, now we have a little problem. The same idea that you understand our equilibrium fractionation and you apply this to presentation was like in the head of Craig and Gordon, two scientists from the 1960s, 70s, and they checked the precipitation using this approach, and it didn't work. They found that precipitation is a bit off. it has more deuterium, it has a deuterium excess. Deuterium is, so it works for O18, but it doesn't work for deuterium. There's a little shift in it. And the excess was plus 10 per mil. So if you take the equilibrium values that you calculate for the oxygen isotopes, you take them for the deuterium isotopes, you put them into this graph. This is the theoretical line. Precipitation will actually be a bit higher, the real precipitation. And there was a big question of why this is like this. So they didn't know. There was a deviation from theory, equilibration theory, of plus 10. This was called deuterium excess, and there were some ideas that you have a deuterium source, and there was something going on, some emanation of hydrogen whatsoever. The solution was that there is another fractionation mechanism, and this second mechanism gives us access to even more understanding of what happens in the water cycle. When I just look at something in the bottle, this doesn't matter. So, like a closed system in a bottle will work perfectly according to theory before the coffee break. Yeah? But if we have an open system and there is actually wind, we have a different situation. We actually have the impact of an interface layer that intervenes here. We have the water, we have the atmosphere, and above the ocean or above the lake, we have a small layer which is saturated with vapor, and water molecules that leave the water need to get through this layer. And this little layer actually creates a deviation from the theory by diffusion. And this opens a new chapter. We have talked about equilibrium fractionation that we understand, I hope. It's clear, the equation dEF, we can calculate this for different temperatures. Now we have a new chapter, and these are the non-equilibrium fractionation mechanisms, which are basically two that we will deal with. One is diffusion, and the other one is an emptying reservoir, a reservoir that is finite and that actually depletes. Let's start with diffusion. So when we look at two different molecules that evaporate from a water body, I have to be self-aware and think of the online audience, not to actually go too much into the screen. So when we have two molecules that we watch, of course they have different weights, and we can express the velocity at which they will travel through this interface layer, which is basically based on energy. So these molecules have energy from the Boltzmann equation, depending on temperature, and this energy can be converted to kinetic energy, so movement, with 1/2 times mass times velocity squared. E equals 1/2 times mass times velocity squared. So you see that the velocity that the molecule has depends on its mass for a given energy. This is clear. Now, if we use this and apply this to both isotope molecules of different weight, we come to a difference in the speed that is in proportion to square root of mass B, which is vapor, the one isotope, to mass A. And this gives us a fractionation coefficient for evaporation, for diffusion. Let's start with that. Now this can be tested, so you can actually calculate this and do experiments, and it works in a vacuum, in an empty atmosphere, when you don't have other molecules. So fractionation of two molecules that have different weights, or two molecules with different weights will fractionate according to square root mB divided by mB. However, it's not realistic to assume that we have vacuum. I mean, this can be used to calculate how much hydrogen or vapor is leaving Earth. There will be a little fractionation effect, and actually we have calculated, there was a scientific question, is does Earth lose vapor and how much? But the isotopic effect that we have since creation of Earth is very, very small. So luckily Earth loses very little vapor to space. Yeah? So this will be the first equation. The second equation is much more interesting. This is the fractionation that you expect when you have diffusion of molecules through a real atmosphere. And I took our dry atmosphere here, which is 72% hydrogen and 28% oxygen. So if we now look at two molecules of water, hydrogen, oxygen, the fractionation that we expect is in proportion to square root of mb multiplied with an A plus 28.8. It is the weighted molecular weight of nitrogen plus oxygen of a dry atmosphere. Yeah? Divided by mA multiplied with mb plus 28.8. Now we can use this to calculate a theoretical fractionation that we get when water evaporates into a dry atmosphere. So when we have a water body, a lake, and it evaporates. Now coming back to our framework questions, we want to understand salinization. This is where we want to go. And we have seawater encroachment. We already saw that the isotopic composition of oceans is known. You can use that. But the second mechanism is, of course, that one of soil salinization, of evaporation of water bodies, of sap gas evaporating, drying up. And of course, you will get enrichment of salt, you get hydrogeochemical processes, you will learn about this tomorrow from Kinate. But we will also have strong isotope effects, and we want to understand these isotope effects. Let me just move the window here. Now, the first equation for vacuum, the second equation for dry air, they are theoretical equations. They give us a framework. Because in reality, our atmosphere is never dry. We always have humidity of more than 50%. So it's very rare that in really dry deserts, when you have a sandstorm or a dust storm, you get maybe humidity of 20–30%. But then you need to drink 5, 6, 7 liters per day to not actually dehydrate. So usually we have always humidity. And the equation that was developed for humid air, evaporation into humid air, is from Gonfiantini, and it's given below. So the fractionation, the E, you remember, this is the isotope change looking at deltas. By evaporation, the kinetic fractionation of water to vapor depends on 1 minus H, and H is the humidity, multiplied with the density of the one isotope divided by the total density of air minus 1. So this is basically now the first really useful equation, and it can be used now to calculate the isotopic impact of evaporation. Now, when we look at our deuterium, oxygen deuterium diagram, let's try to move the window, and we again look at the O18 deuterium diagram, we have seen that there is such a straight line that corresponds to the equilibrium. I have told you that we know that the real line on which we find evaporation is +10, has a +10 excess of deuterium. So this is the normal line that we expect for precipitation. And when we have evaporation, we will actually get a U-curve, and this is the evaporation curve that you see here. The evaporation line has a lower slope. You see it here. So this happens when you evaporate water. This will be the original composition of water before you evaporate. And we know already equilibration in the atmosphere creates samples that lie along this precipitation line. When it's cool, when it's winter, it's lower left. When it's warm, it's higher up. When we are in a closed system, the line goes through a point that we have 0, 0. Doesn't have deuterium excess. So it goes to the point 0, 0 for CO. When we have not a closed system, when we have wind and when we get this interface layer, our line shifts higher by in excess of 10. So this is our precipitation line. It has a slope of 8. The slope 8 comes from the differences in equilibrium fractionation between water, oxygen 18, and deuterium. Now, once we start evaporation, this is the unevaporated water, the rainwater. We actually get an evolution along the evaporation line. The evaporation line has a slope lower than 8. And we can calculate the slope actually using these two small formulas by Gonfiantini. Gonfiantini has suggested that the isotopic change that happens because of evaporation, in addition to equilibrium, is E for O18, 14.2 times 1 minus humidity, and for hydrogen is 12.5 times 1 minus humidity. Let's do the test. Let's assume we have 100% humidity. Then this will cancel out. Then we multiply with 0, and we don't have any additional fractionation or isotope effect because of evaporation. So when the atmosphere is fully saturated or close to saturation, we just have values on this line. But when the atmosphere into which we evaporate has a humidity of less than 80, basically 70, 60, we get an additional isotope effect. Then we get evaporation, because with 100 you don't have evaporation, and we get an additional isotope effect, which is stronger for O18. So we calculate our epsilon, our isotope change first for equilibrium, which just depends on temperature, closed system. And then we actually add a second effect that is related to evaporation. And this gives us now a new line. And the stronger the evaporation is, the more our samples are away from the center along that line. So usually when you take samples, you have several points that are not on the line, and you create a regression line that goes through your evaporated points. This works if evaporation happens in the same atmosphere. I will just show you an example from my own PhD. These were samples that I took in the Kalahari, where you have a lot of evaporation. And so this is a very homogeneous environment in which evaporation took place. So you see, obviously, this is the line where we expect the precipitation to be. It has usually a slope of 8. 8 is the ratio between the change in the isotopic values of hydrogen compared to oxygen. So this fractionation is, if you want, 8 times higher than this one. And these samples are all from evaporation. They are all from a region in which evaporation is very strong. You put a regression line to it. And the regression line now gives you a new slope. I think I have, yeah. So the slope is usually 4.5. You can determine it. And now highly evaporated samples are located here. And almost not evaporated samples are located here. Now, the slope depends on humidity. So the drier the environment is, the lower the slope gets. And you can even calculate a theoretical value. This afternoon we'll run an example where we do all these calculations ourselves. You can even calculate the theoretical value of the evaporation slope, which is quite interesting because it cannot be lower than 3.5. Yeah, so there's a lower limit, and it's interesting because you get publications where you have slopes lower than 3.5, much lower than something else has happened that is not evaporation. So there's actually, even when you have a very dry atmosphere, there is a certain point below which you can't get. Yeah? Okay, so now what can we do with this? The first thing is we can detect open water evaporation. We can detect samples that have undergone evaporation. Now some questions and answers. This only works for open water. Evaporation from soil is not always visible. Evaporation, let's see it like this. Evaporation through plants, transpiration is not visible, unfortunately. Yeah? There are some minor isotope effects. We have studied this that happen during interception, and the roots do a little bit. But basically, plants avoid fractionation. Why? because they have stomata and they work like this. They fill, open, close. So they have no permanent leak. And when you operate a mass spectrometer, you do the same. You always have valves to open, close. You transport gas like stepwise to avoid fractionation. And plants somehow have learned to do this as well, maybe for a reason. So they actually open, close, and they avoid fractionation effects. So, but you can determine open water evaporation from sep gas, from lakes, and you see this clearly in the isotope signal. Now, this is what is done in many papers, but I want you to go a step further. When you fit a regression line to it, you determine the slope, and you can actually, with these two equations, calculate the humidity at which evaporation took place. And this is interesting. Yeah? You get an H that actually explains the fit of the curve. Yeah? So this is quantitative isotope hydrology. Not just saying there is evaporation, but determining the humidity. And of course you can calculate the degree of evaporation. Is this clear? Did this come across? Evaporation line, more or less? So let's summarize a little bit. Basic thing is equilibration at a certain temperature. This explains closed system fractionation. When we open the system, when we have wind, we get deuterium excess. This is typical for rainfall. So the empirical observation is that we have a shift of +10 in real systems. There's even an anecdote to it. In the Eastern Mediterranean, in Cyprus, Israel, Jordan, the shift is not +10, it is +20. The Mediterranean is special because it's a semi-closed sea, and the semi-closed sea has its own isotopic signal, and which is called Eastern Mediterranean waterline. So in the Eastern Mediterranean, you have a shift of +20 that you see in Cyprus. So in Cyprus, you will actually see rainfall that comes from the Atlantic has +10, and rainfall that comes from the Eastern Mediterranean has +20, which is interesting because you can determine how much rainfall stems from internal recycling in the Mediterranean and how much rainfall comes from external input into the Mediterranean. Yeah? Once you have evaporation, the slope will not be 8 anymore. It will actually be lower than 8, and the lower the humidity, the lower the slope is. Yeah? So we can practice this afternoon. I think, no, it's this one. So I've prepared the calculations for this in R, so that we can calculate this ourselves. And we will do an exercise where we calculate basically the initial delta value, then we calculate the equilibrium value, and then we calculate the epsilon that we get from evaporation to predict the final one. And we do this for OIT or deuterium, and by doing this, we can actually create an evaporation line ourselves for different humidities. So if you want to do this in a practical example, you can actually prepare a diagram where you a nomogram where you pre-calculate the evaporation lines for 80, 60, 40%, and then you plot your data inside, and you see immediately at which humidity the evaporation takes. Then you can compare: is it does it correspond to my meteorological measurements or not? And if it doesn't, you know that this is a paleo system or evaporation took place at a different location, not where you thought. Okay, now we have a second process, and this is the final one, and then we will go into applications and discuss these applications. And this is also a kinetic fractionation that is called Rayleigh fractionation. Rayleigh fractionation. Who knows this term already? Rayleigh fractionation. It has to do with whiskey. Lord Rayleigh developed this because he wanted to describe the process of fractionation of alcohols, good alcohols and bad alcohols. So when you make whiskey, you try to remove the methanol because it's not good for your eyes and for your health, and you actually try to distill the alcohols, and he observed how well the distillation of different alcohols worked. And so he developed this equation for the distillation of alcohols. But you can apply the same equation to the distillation of isotopes during a reaction. So you have heavy isotopes or a heavier alcohol, or alcohol that has a higher boiling point. And you have another isotope that behaves differently. Now, how does the equation look like? We have R, which is the isotope ratio at the end of a reaction, and we have the initial isotope ratio. Now we need to work with R's, not with deltas. This equation doesn't work with deltas. And we have F, this is nu, and F is the fraction. So this tells you, in our case, how much water has actually been processed. So this can be, if you have a calcite that precipitates, how much calcite has precipitated. If it's water that evaporates, how much water has evaporated. If it's a cloud that is raining out, is how much water rains out of the cloud. So how much is left. So this equation applies always when you have a finite volume that is consumed by a reaction. So this happens or applies when you have a lake that evaporates, empties, or you have a cloud that has rain out. Or you could also use oil that is actually remediated by bacteria who eat the oil. But they prefer to actually first degrade the light carbon isotopes because they need less energy for this, and they will fractionate the oil isotopically. They will first rather process the light isotopes and then the heavy isotopes of carbon. By monitoring now the change in isotopic composition, you can determine how much of the original material bacteria have processed, or how much of the lake has evaporated, or how much of the calcite has precipitated, etc. So it's always when you have a finite reservoir and a reaction that depletes the reservoir, and when you have a fractionating, when this reaction is fractionating. I just want to demonstrate this and also to connect this to what we have done before. Let's assume we have rainfall and vapor, which stems from the ocean, has a value of 0. Now we actually look at the precipitation. So we have rainfall being created from the cloud that comes from the ocean. Now, when it rains for the first time, let's say at 20 degrees, we will actually have an isotopic change of 9.8. We can calculate this with the alpha delta calculator that I've shown you, or by getting the DEFs and calculating this isotopic changes. The rainfall is actually, let's see, the rain vapor. This is rain vapor. This is the vapor. So we start with -10, and the rain is 9.8 heavier. So this is the first rainfall. Now, what is new now? When we look at oceans, oceans are infinite. So the amount, they are not infinite, but the amount that we actually evaporate from the oceans is very small compared to the total volume. So the isotopic composition of the ocean will not change because of some evaporation. However, if we have a cloud, it's significant, because the water that we lose from the cloud will actually change the isotopic composition of the cloud itself. Because of that, now, not only the rainfall has a fractionation, also the cloud will be depleted of the heavy isotopes because they fall out of the cloud. And with that equation, we can now describe how the cloud will actually change its isotopic composition of the remaining vapor. This is the gray curve. And how the rainfall will change when the cloud is depleted more and more and more and more. Yeah? Here is a little change because we have 0 degrees and we now get snow. Yeah? Now, the equation that we use for that is the Rayleigh equation. We have to convert deltas to R, otherwise it doesn't work, otherwise we cannot work. And we can now use this equation. You see the alpha, which is the fractionation factor. You know how to calculate it. And now we can, for example, solve for F. So we can calculate the fraction of the lake that has evaporated when we know the initial R. I have checked this myself. I took rainfall from Spain and then across Europe up to Russia, and I plotted them and I applied the model to describe how the rainfall composition will change from the Spanish coast to the Ural, to the mountain range in Russia. And you see that there is a perfect match. So we can actually calculate the continental effect that we use so often. We can calculate how the rainfall gets more and more depleted when we are further away from the coast, based on a physical relationship, based on a clearly defined equation. But we could use the same equation to calculate how much water is left in the lake, for example. Did this come across? Yeah? Okay. Now, just to explain this a little bit, the example, we apply the Rayleigh equation, and the F is basically a water balance. So we have the flux of vapor into the continent QA. Then we have the integral of the precipitation, so all the precipitation that fell out of the vapor flux, plus the evaporation. This is the evaporation that happens between Spain and Russia. And if we divide this again by the total flux, it gives us the fraction of vapor that came into the continent that is left, that was not actually created as rainfall. And by doing this, we can actually even solve hydrological water balances. Yeah? So this is practical. Now you can actually convert the F for a lake. So you take the inflow into the lake, the loss by a lake, and then solve the equation, and then you get the water balance of the lake. So this is actually very, very useful, because you don't need 20 years of measurements of the lake, of water levels, and Penman-Monteith equation and meteorological station. You can actually do this based on the isotopic composition if you know the R to start with. Okay, so we are almost done with the principles, with the theory. Now we will go into applications. The last one is one that you rarely find in textbooks. It's not published in most of the textbooks that we have, and I think it's very interesting. Looking back, I showed you that we can use isotopes as a thermometer. We can use it as a hygrometer. And I will show you now how it can be used as a clock. And there's one effect that is quite astonishing and that is useful. And this is what happens when you, I have two bottles now, and I need something else that I don't have. So you imagine, now these two bottles, I will open both of them. They have different water. So one is actually water from the Alps and one is water from Salento, let's say. And I will put them now into a closed box, into a new atmosphere. So imagine just a glass box around these two bottles, and remove my hands so that it's really closed. Yeah? So when we let this stand now for 2 or 3 months, we will see that the isotopic composition of the water in the bottles will become the same. I mean, this is maybe not so surprising. We have initial values that differ quite a bit, and we evaporate. This goes into an atmosphere, and it's a proof that there is a permanent evaporation. It's not a one-way process. There's a permanent exchange between vapor in and out of the bottle, and as a result, the isotopic composition will equilibrate. But this is a rather slow process. It really takes months, weeks and months, and this can be used as a clock. So we can use this to measure time of equilibration between hydrological systems. Because this process is defined by an equation, so we have the isotopic composition in the isotopic separation, if you want. And I will not go into all the details, but the key parameters are the surface of water in both reservoirs compared to the volume. So this would be very bad because we have a small surface compared to a large volume. So with this configuration, it will take very long. Yeah, when you have a very flat, it's much faster. And then the temperature plays a role, of course, the pressure, but the key is the surface volume reservoir. How can we use this? We could use this, for example, to estimate vapor water surfaces in karst systems. So we cannot look into them in soils. So I think just the physical process is interesting because it gives us tools to work with. Yeah? So this is the theory, and now I would like to apply it. So just a short summary, we have looked at equilibration, you should be able to calculate it. Diffuse fractionation by evaporation, radial fractionation, like depletion from a reservoir, and the last one was equilibration between two reservoirs. And all of these processes can be calculated. And now I would like to put this into a context of salinization studies and how we can really use this. So, first is an example where we have strong salinization. This is from Brazil. Northeast Brazil. We have, it's a region with water scarcity, and we have taken samples from groundwater, from surface water, from precipitation, and from reservoirs. And you see here that most of the samples are on the precipitation line. The good thing is this works worldwide, more or less, and you see some of the samples, and the ones that were taken from groundwater, especially are evaporated. So we see that the groundwater has evaporation signals. So this was very interesting because this was something we didn't expect. We thought that we didn't know that the water was actually salinity in the groundwater was stemming from evaporation. Yeah. So salinization, we have to, just to make a small tour d'horizon, can be seawater encroachment, can be evaporation from soils, the soils get salty, and the salt is washed into the groundwater. Could also be that groundwater has discharge zones and evaporates in these discharge zones. As long as it just evaporates, it doesn't make the rest of the groundwater salty, but if you have a lower water pressure because of abstraction, the salt can be washed back into the aquifer. And then we have a long number of other processes. So you can have water-rock interaction, dissolution of salt. So there is salt in the system that you dissolve. Serpentinization and closed basin salinization. So now it gets very interesting when we combine stable isotopes with chloride, with chemistry. So this is the case. We have here different samples. And these are different reservoirs. So we see that we have isotopic compositions that are very positive, which means we have strong evaporation from all the reservoirs. And the chloride concentration is still quite low. So we have less than 500 milligrams of chloride in these, although we have high evaporation. This means that the reservoirs itself have strong evaporation, but the evaporation creates a strong isotope signal, but the isotope signal is not the primary cause of salinization. Because at the same time, these values have, although they are very enriched by evaporation, still values below 500 milligram per liter. But the groundwater, which has moderate evaporation signals, now has elevated chloride. So the combination of stable isotopes with chemistry, with chloride, is interesting because it tells you, and I will show you an example from the Metzal site, Mersin. It shows you whether the salinization is primarily caused by evaporation, because then you would expect that these are shifted to the right. Or whether there is an additional second mechanism bringing salt into the system that is not only related to evaporation. So I'm just checking for the Mersin example. Sorry for that. So this is the example from Mersin that we have. This is Turkey. So here we have actually applied this combination. We put together the isotope signal. I will show you the isotopes first. So these are the stable isotopes from Turkey. We see that, first of all, the total values are quite depleted. We have values between -6 and -10. I have plotted the precipitation lines of the global precipitation line. This is where we expect global precipitation to be, which is 8 times the O18 value plus 10, which is the deuterium excess. And I have plotted the eastern Mediterranean waterline. This is the typical precipitation that we find in the eastern part of the Mediterranean. This is a precipitation that stems from vapor that was generated from the Mediterranean itself. So in Turkey, we see, first of all, that the isotopic composition is close to the eastern Mediterranean water. This is not very surprising, but it's interesting because it shows that the rainfall is derived from the Mediterranean itself, from the eastern Mediterranean. There's one example where we get some inflow from the Atlantic, so there will be probably more samples, but at least the groundwater that is created, because these are groundwater samples, stems mainly from rainfall that is from the eastern Mediterranean. We have also the seawater. The seawater now has the value of +1 and 0. So this is close to what we expect. We expect 0, 0, but of course there can be small differences. So this is the seawater sample. Now we see that the water from Turkey doesn't have evaporation. There is no evaporation signal in the groundwater of the study site that we have in Turkey. This is quite interesting, quite revealing. So break is from 12 to 1 or 1 to 2? 1 to 2? 1 to 2, okay. Now we add salt. So we now, like in the previous example, we add a chemical parameter. Here, in this case, I've chosen to take the deuterium excess and the electric conductivity. So electric conductivity is clear, it's the total mineralization of the water. Here I have chosen to take the deuterium excess. The deuterium excess is how much extra deuterium you have compared to O18. I told you that for full equilibration in a closed system, we expect this to be 0. I told you that for precipitation, usually it's 10. And that in the eastern Mediterranean, it's 20. So the deuterium excess is at this point where you end. So normal precipitation goes through 0 plus 10. When O18 is 0, you have a deuterium of 10. We expected basically 0 from the equilibrium fractionation. In the eastern Mediterranean, the deuterium excess is 20. So at 0 O18, you have 20 deuterium, so you have plus 20. This is the excess. Do you get this? Now, I plotted this excess. Yeah? Why did I do this? First of all, I see whether this is precipitated water and whether it comes from the Mediterranean or the Atlantic. But then when we have evaporation, look what happens. If we have evaporation here, and we create a new evaporation line, it will make our deuterium excess more negative. So when we take this water and we evaporate it, we will get an evaporation line that has a lower slope. And the slope will cut to 0 at a value below that is much smaller than 10, and that could even be negative. I would like to have a board to show this more clearly. Now, what we see is, this is the deuterium excess, it's between 14 and 19, and we see clearly that there is no evaporation in the groundwater. And the elevated salinity that we get does not come from evaporation. It is just added to the water without changing the deuterium excess. So this is now a clear indication that the salinization is not primarily due to evaporation. We see this twice. We don't see it in the O18 deuterium diagram, we don't see, there's only one blue point, and this is seawater. But the groundwater, the red dots, are not evaporated. The groundwater in Mersey is salty in some areas. We have some salty samples there, but the salinity does not stem from evaporation. This is clear. And we see that the elevated electric conductivity has nothing to do with evaporation. So this is actually an analysis that you can do to check whether evaporation losses are a significant contribution to your salinization. So this was the first application. So when you want to use isotopes in the context of salinization, take your samples, analyze them for OIT and deuterium, check whether you see deviations from the precipitation line. Then you can even make a linear regression, determine the slope. From the slope you can determine the humidity at which evaporation took place. You can calculate the degree to which evaporation took place using the Rayleigh fractionation. So it's obvious the more you are towards the right on that slope, the more evaporation you have. You can even quantify it using this equation, the Rayleigh fractionation equation, and then add chemical data and check whether the evaporation is somehow connected to increase of chloride. If you see a connection, a correlation, then you know that evaporation is the primary process. If you don't see it, it's not the case. Yeah? So that's how we can actually do this. Now there is another small analysis that I learned from Nebo Sky, which I would like to share because it's a very nice method and very useful. And this is the calculation of the original isotopic composition before evaporation took place. If you know some mathematics, it can be derived very easily because it's just the equation that you have for the intersection of two straight lines. So you have the precipitation line and you have an evaporation line. And you know the slope of both lines because you can determine this from several samples. And then you can actually calculate the intersection point. I just want to show this point here. This is the point corresponding to the original water before it was evaporated. And it is very helpful to know the isotopic composition before evaporation. And this point can be calculated using this formula, in which the evaporated sample has DH, deuterium value measured. You have the slope of the evaporation line that is called E. You have the measured OIT value, and you have the deuterium excess D, and the slope of the normal precipitation is 8. And so doing this, you can correct the OIT value for any sample that is evaporated. So you can calculate for any sample that you have how it looked like before it evaporated. And this is, of course, very interesting and helpful because you can then use this original value to, for example, estimate the elevation at which the groundwater was recharged. Yeah? Okay. So here, this is where I apply this. I have all these samples. This is nice, but I wanted to know, where does the evaporated water come from? Does it come from the ocean, further evaporation? Does it come from the mountains? And so this is actually where this formula applies. Second application, we are in a location at the coast, and we would like to know where the saline water originally comes from. So, if it's evaporated, we remove the effect of evaporation using this formula. Yeah? Now, this is the first thing that we do. The second thing is we try to use the elevation effect that I had introduced in the beginning. I told you there are three major macroscopic effects: seasonal effect, elevation effect, altitude effect, and continental effect. Now we have verified this. This is an example from Cyprus, where we have actually sampled water at different elevations. You see the altitude on the right-hand side from 0 to 1,750 meters in each orders. And you see our samples. And I have added two lines, limiting lines for these samples, and two different groups of waters. Basically you see that if you look at the upper group, that there is a dependency of the isotopic composition from the altitude that you have. So there's a kind of band, which means isotope values get more depleted with higher elevation. And this elevation effect can be calculated, and you need to do this as a kind of regional study. What the elevation effect is, usually it is between 0.252 and 25 Kelvin per mil, sorry, 0.25 per mil per 100 meters. So doing this, for example, if we have a site with saline water, we have corrected the original isotopic composition, we can actually recreate the elevation at which the groundwater was recharged and created. Yeah? So if the value, for example, is minus 8, and we have an elevation effect of 0.25 per mil per 100 meters, and we have a coastal value, the coastal groundwater has a normal value of minus 6. Yeah? We know that the recharge took place 400 meters above the coast. Yeah? So here we have elevation. We can now look at this line. So at 1,250 we have minus 7.5. And at 250 we have minus 5. So this means 1,000 meters difference translates into minus 5.2 minus almost 7. So it's 1.75 divided by 10. So this is 0.175 per mil per 100 meter change. So every 100 meters in higher elevation of our recharge zone, our isotopic composition will be minus 0.175 lighter. We can measure this with a precision of more or less minus 0.1. This means that we can distinguish differences in elevation of less than 100 meters. Yeah? More or less. So this is actually very useful information because you can determine of which elevation your groundwater comes from. Yeah? It will not work very well in Salento because here the differences are quite small, but it will work very well, very well in the Alps, but also well in Rhodope, where we have a study site. It will work well in Samos. It works very well in Mersin. So whenever you have elevation differences of more than 500 meters, I would say it works well. Okay, so this is something already for the exercise that we did. I think I have prepared this for the calculation of C13 values, and we will do this in the context of carbon-14 dating, and I think we will do this together with the exercise. This is better. I want to shed light also on some other isotope systems, because basically it's a good approach to use multi-isotope studies. In this case, we could also apply a quantitative approach, but I will first describe how we just do this in a qualitative manner. So when we have high salinity, it could stem from seawater intrusion, from upconing, from evaporation, but it could also stem from use of salts in agriculture. In one of our study sites in Bordeaux, we have actually a closed basin effect. Due to intensive cotton farming, groundwater is extracted from the coastal aquifer. You have a lowering of the water table. The water table is below seawater level. This doesn't necessarily immediately cause seawater intrusion because you have low permeability of the rocks, but the water cannot drain to the sea anymore. So actually the water is trapped. You have a closed system, and all the inflow of groundwater from the mountain front recharge will stay in that closed basin, will be pumped up, used by farmers, irrigated, trickle down, will be repumped, irrigated, trickle down. Every year you lose part of the water due to evaporation. So you enrich salts, and if you look at the purely mass balance of this thing, the nitrates and all the salts that come with the groundwater flow cannot go to the sea. So the export of salt, of nutrients to the sea is zero, because you don't have a gradient. And this is a type of salinization that is called closed basin salinization. You get an enrichment due to agriculture, addition of fertilizer, and addition of salts with a zero flux of the salts and nutrients to the sea. I think this is a very, very important process in the Mediterranean, and the following method can help us to actually identify whether this is an important element to it. You see here the isotopic composition of nitrogen, delta 15N, measured on the nitrate isotope. So when you have a compound-specific analysis, you have this notation. You have the isotope, delta 15N, on the compound nitrate. You could do the same thing on the compound N2O, or you could do the same on nitrite whatsoever, or on ammonium. But usually you do this on nitrates. And here you see this is the 15N, and here you see the delta O isotopic signature on nitrate. So basically with this method you measure the isotopic composition of nitrogen in the nitrate compound and of oxygen in the nitrate compound. Now, the first study that has been done on this methodology was by Susanne Verkelius. It was published in Nature, and she took samples from many agricultural fields and from different sources of nitrates. For example, manure, mineral fertilizer of different production, from natural organic material, and you can also use sewage, human sewage, or manure, compare this. And she observed that these different sources of nitrate have different isotopic signatures or fingerprints. So if we just look at the nitrogen bar, delta 15N, we see that the ammonium fertilizer has -5 to 10. Again, here we have a reference sample, delta for nitrate, and compared to that reference sample, we have a depletion in ammonium fertilizer. The soil has a value between 0 and, we could even say +5 and +10, and sewage, human sewage, has a value of +10 and more, towards +30. It is very interesting now to look at the second dimension of this isotope, to look at the O18 values in nitrate. So the mineral fertilizer that farmers usually apply in such systems is different in terms of the O18 isotopic composition. It's a value of around 20. So you can clearly distinguish mineral fertilizer from soil N and sewage using the O18 information. And the NO3 and rainfall is again different. Now in this diagram, you basically work like that. You just use such a standard diagram and you take the sample and you put the values into the diagram. And then you actually assign a specific source area. And this helps you basically to identify the application of mineral fertilizer, to be really sure this nitrate comes from an agricultural source. You can distinguish organic fertilizer and mineral fertilizer, and you can determine natural sources from artificial sources. So this is the basic application. There's a second application to this, and that is in the detection of denitrification. So denitrification will actually induce a change that follows the arrows. So if you have denitrification, you get an evolution along the arrows. So you need to take more samples from the same hydrological system to be sure, but when you have an evolution along this, then you can be sure that this is a denitrification. So this is useful, especially when you think that your salinization mechanism is not natural, it's not seawater intrusion, it's not dissolution of salts, it's not evaporation, but that you have a closed basin nutrient trap mechanism that is associated with intensive agriculture. Because in that case, I would check now for the source of the nitrogen in that system. Yeah? Do you have questions regarding that? Yes. I mean, have you been familiar with this? Have you seen this before? Yeah?
To understand exactly what they want to ask you, if from this diagram, you will see that when we have some values between this for fertilizer, for sewage management, they take some values between, from the diagram, from 0, and we can understand whether it's from fertilizer or it is natural or it is from seawater.
Yes, basically we can say that, and this applies to many different isotope systems, and this is a very common application. Usually you build a database of samples. So in this case, Susanne Fekelius has built a database of fertilizers. You can make the database better by adding fertilizers from your specific region. So you get values from farmers, from manure. We have actually asked farmers to send us samples from Poland from manure, from mineral fertilizer, everything. So we made a database specifically for our region. So you can actually make these boxes a bit narrower, or shift them a little bit. When you're sure about the boxes, you actually take groundwater samples and you plot them into the diagram. And then when these samples, if you take coincide with the box, you know about the source of that specific fertilizer.
Something empirical. It's something from a database, data that have been collected.
Yes. So if you start from scratch, you would use such a diagram from the literature. But I would be very careful to check from where does it come, that you don't make a mistake. So if it's from the Mediterranean, it's perfect. If it's from Europe, it's more or less okay, but you have to double check. But you should not apply such a diagram for Namibia if the data have been collected from the United States. So when we apply this in Namibia, I actually try to make a new diagram just for Namibia. Yeah, but like for Italy or for Greece, it would work on the European database, basically, because we have similar sources of fertilizer. But of course, it's better to make this more specific. Now we can say that if we are in this sequence here, this is actually, these are all the natural nitrogen processes that we observe involving ammonium, soil. This can be important if you have forest fires or you have a removal of a forest. This can actually create a nitrate push. Yeah? And this will all have O18 values around 0. And we can basically say that the higher we are in our nutrient pyramid, the more we shift to the right. So human sewage is plus 20 around. If we have animals, organic fertilizer, this is around 5 to 10 or 15 because we eat animals, so we enrich the nitrate. And the plants are minus 5 to 0. So you see, actually, this is a kind of fractionation in the nutrient pyramid. Now, these are the carnivores and these are the plants. But if we actually involve chemical processes, like production of mineral fertilizer, we move up in this dimension, we change the O18 value. And the most useful application is to distinguish mineral fertilizer from natural sources of nitrate and to actually distinguish plants or plant nitrate from animal nitrate from human nitrate. Yeah? And by doing this, you can actually learn a lot about your system, and if you have salinization involving high nitrate values, especially for closed basin situations, you can learn whether this is the case. Yeah? Okay. So I would now like to take you through our study areas. Dimitrios Bassoukas has programmed a web application in which you can access the chemical data and the isotope data that we have collected in the MedSal project. So you can access it through MedSal.eu, our webpage, and when you click on the chemistry, you see the chemistry from the study areas, and when you click on isotopes, you see the isotopes from the study areas. And I would just like to walk you through the isotope values that we have, stable isotopes from different study areas. You see the study areas here, Salento, Rodok, Samos, and Mercy, and Fischer is not there yet. Just show you the isotope values, and we want to apply what we have discussed this morning. Yeah? Let's start with Salento. So you always see on the right-hand side all the isotope values in light blue, and the one from the study region are dark. So we can actually now look at Salento. By the way, these dashed areas are the ones in which salinization is known and has been documented in the International Hydrogeological Map produced by UNESCO IHP, International Hydrological Program, and by the BGR, which is the Federal Agency of Geosciences in Germany. So we see that we have salinization here, and these are the samples that are plotted. Now, first of all, we see that the dark samples, we see that we have the Mediterranean waterline shifted a bit higher, it's like plus 20, and we have the Atlantic global precipitation waterline, and the Italian samples correspond to vapor from the Atlantic. So the water source that you get here is from the Atlantic. Second, we see that we don't have much evaporation. So we don't see an evaporation line. So the groundwater that is created here in Salento actually infiltrates quickly through the karst system and did not undergo significant evaporation during the recharge process. This is interesting because it tells us something about the salinization process as well. So salinization doesn't happen because of evaporation at the surface or even soil salinization in wet areas. It has other causes. Yeah? We see also that we have one single sample that is very depleted. You look at the lower left corner, has a value of around minus 11 and minus 10. So taking into account this one, it's one sample. This is from Salento. Now this is very suspicious because this single sample is very different from all the other samples. Unfortunately, it's just one. It's the most depleted sample that we have altogether. You know that this diagram means this is a kind of thermometer. Lower left is cold, upper right is warm. Yeah? So, do you have any idea what this could be? Yes?
Maybe it's from a mountainous area.
Yes? Is this hydrogeologically possible?
No. No, it's not. Sinceramente no.
You have another idea? Yes?
Hello.
Because-
Can you please all use your microphones when you speak up so that everyone can attend?
Yes.
Thank you.
Thank you for the reminder. Wow, this is
The big brother is watching.
Deus ex machina. I should repeat every question that you ask me for the online audience to hear it. Thank you for reminding me, Andreas. So I will do this. I ask you what the reasons are. The first answer was
Altitude.
altitude effect. Yes, altitude effect. Mountain. So mountain. We think this is not the case because we don't see a hydrogeological mechanism or flow path. Now, the second suggestion was seasonal effect. Seasonal effect, yes, it could be that. Did you have snow here during a recent winter? No. So it is actually, it happens when you have a snow event. We had snow also in Jordan, and there were reports about snow in even in Northern Africa, I think. This can actually be very depleted, and you could have such a sample which is just coincidence. Will not be on the long term. So when we have snow events, I always take samples. We collect this because it's as an end member. So yes, this could be a singular effect. But there's another possibility. I'm sure there are more, but there's one very interesting other possibility. What this could have been. Yes?
The continental effect.
Yeah, continental effect was mentioned. Continental effect, yes. This is an interesting point. I need to make a little, to tell a little other story to show how this could be. Now, the continental effect, if we look from the Atlantic, wouldn't actually change much because you don't have a big difference in the flow paths of atmospheric moisture. Now, it didn't happen here in Italy, but imagine the whole weather system would actually come from the other side, and suddenly you have a huge continental effect. This didn't happen in Italy, so this is not the explanation, but it happened in Jordan. Now we have air masses basically coming, it's called Red Sea trough. They come from the Atlantic, and under certain conditions, they travel through the Red Sea, but this is Atlantic moisture. They travel to Jordan, and there you have heavy rainfalls. It's Red Sea trough events. But in the past, like 7,000 years ago, 5,000 years ago, we had weather systems that came from the east. So moisture came from the Gulf Sea, and then you had a big continental effect. And we find very depleted water in Jordan that you can never explain with continental effects from current weather patterns. So we have a kind of proof that the moisture, when we had much higher rainfall and recharge, came from the other side of Jordan and had a continental effect. We published this in 2003. So this is actually a reversal of weather systems can be detected in some cases. So this is an interesting possibility that could play a role. But there's a fourth possibility.
The age maybe from background.
The age. Yes. So it could be that this is a remnant of a cooler period where we have different rainfall, different temperatures, different ambient temperatures. The water could even be very old. We have another 45 minutes about residence time. So it could be very old, and this is probably the case here. Alessandro?
It's from Lago Rosso, well.
Yes.
Ah.
So this could actually be a paleo water.
Paleo water, the salt paleo water.
Exactly. So actually, you see here that paleo waters can be detected with stable isotopes. Paleo water is a water that was created under completely different conditions. It doesn't participate in the current hydrological cycle flow system. It stems from another hydrological cycle or flow system that was probably activated, created under different conditions. And often you see paleo waters because they have very different isotopic compositions, also unstable isotopes of water. So this is actually already very interesting finding. Now if we move to Samos, you see now also from flipping between the samples that this, yes?
I would like to ask
Yeah, yeah. Yes, I will repeat your question.
I will repeat my question. Basically, I have another question regarding this outlier in the sample. At what depth these samples were collected? Because I can imagine that paleo water can be found very deep.
Minus 150 meters above the mean sea level.
Yes. So, yes?
And where is it located? Where is it?
In the middle of Salento area, near Galatina.
Ah, interesting. Okay. I would like to discuss with you later.
So let's move to the next area. So now the comparison between the different areas is very interesting. We see immediately that we are on a different isotopic water line. We are now on the Eastern Mediterranean water line. This means that Samos receives most of the rainfall from internal moisture production from the Eastern Mediterranean. So this is re-evaporation of water from the Mediterranean. This is the first lesson that we learn. Then we see that we are further to the right. So we have the values are a bit heavier if we compare this to Salento. Yeah? No, this is wrong. Now they are the same. So you see they are just shifted. I just jump here up. They are just shifted up. So we have a different moisture source. This is interesting also for climate change aspects, because we know that Samos depends on internal moisture production. So if we have now some changes in the weather system, global circulation patterns, it might affect Samos in a completely different manner from Salento. But this is another story. But now we also see that we have evaporation. So we have several samples on the upper right. And now we see, I said before, we don't have significant evaporation. This is not completely true here, because if you extend this line here, you see that the samples, the upper samples, deviate. So here we actually have a significant impact of evaporation of the upper right samples. They have been created by evaporation. This is consistent with the hydrogeology. We have wetlands and we have glyphadas. So we have salty lakes with surface water that causes evaporation. Now from these samples we can actually make a backtracking to find the original isotopic composition of the source water before the water became saline in the lagoons. So we know from where the water comes, what the original source is, and we can compare it to the other sources. So in this study area, we really have an impact of surface area, surface storage, evaporation from discharge zones, soil salinization that we saw also. You see like white soils that are salty, and when this is washed into the groundwater, this is the salinization mechanism. The intrusion mechanism, encroachment of seawater, is quite weak in this area. This is different information because we have a very strong push of groundwater from the mountain area, where we have quite a lot of groundwater recharge. Let's move to another region. This is now Mersin. So we see we jump first further to the left. We have cooler signal, bigger spread. In this area in Turkey, we have high mountains that have snow melt, and we have mountain recharge that is found here. So it could be that we also have paleo water. If we look at the lower left, we have again single water. This has to be checked, comparing and using the other chemistry. It could also be related to a high mountain recharge. We see that we have both weather systems active. We have the Eastern Mediterranean, the upper line, and the Atlantic. So this region also receives inflow of Atlantic moisture precipitate. We don't see a strong impact of evaporation, although we have lagoons and we have canals. This was a big lagoon area, but we don't see actually much of that impact. This is quite interesting. We have some samples that are very strange because they are above this 20 line, for example, this one. I didn't talk about this mechanism, but I think with your knowledge of principal isotope fractionation processes, you can get there. There are some fractionation processes that only affect one isotope, not both. And one of these is geothermal processes. In geothermal systems, especially when you have methane, the methane production can change the isotopic signal. Methane and hydrogen can change the isotopic signal of only one isotope, only the hydrogen, without changing the oxygen. And when this happens, you will have evolution just upwards. We look at two isotopes at the same time in this diagram. And if you have one fractionation that just affects hydrogen, it will just move up or down. And actually, hydrothermal systems that have methane and hydrogen are have often observed to have an upward shift of the isotopic composition of just hydrogen. So this would point to geothermal processes. By the way, we also see this in waste dumps. When you have a waste dump with methane and hydrogen production, then you can actually have, could also be a waste dump water if you want, but then we have to check this with other. This is a local effect, but usually this is associated with geothermal systems. Yes, we have discussed this one, and this was just the application of the principles that we had discussed so far to consolidate the knowledge. Do you have questions? So what is your feeling? Do you get familiar with the concepts step by step? More or less? So we'll train this afternoon. So we'll do some calculations of isotope values by equilibration. We will actually practice to calculate evaporation effects, to calculate the Rayleigh fractionation, so that you get, based on the theory, more familiar with the practical aspects also. Do you get more familiar with the interpretation of these phenomena? Slowly. So the summary of the principal things, the most important things, when we have evaporation, we see it clearly in the deviation from the precipitation line, which has a slope of 8. We get a new slope that is lower than 8. The lower the humidity, the drier the environment, the lower the slope is. Usually it's around 4.5. A combination of stable isotopes with chemical data is very interesting, because we check, for example, whether signs of evaporation correlate with signs of salinization. And this is the case. We know that evaporation is a cause. We had already mentioned the topic of residence times before, and I would now like to discuss how we can actually determine the age of water, the residence time. I would very much like to have a board now. I think I can draw on this one, but I don't know whether this will be shared, so I better don't do it. We will now discuss how residence times can be determined, and I will introduce methods that range from weeks to 40,000 years. So the overall spectrum of isotope residence time determination methods ranges from basically even hours to a million years. So this is what we can cover. I will not cover the methods of more than 40,000 years, because this is only applied in very dry deserts, in Jordan and in Australia. like big. So this is a very, very special topic. I will cover methods that range from weeks to 40,000 years. Yeah? And let's start. The first method that you can use to determine whether your hydrogeological system is active, is pulsating, is to use the variation of the stable isotope value itself. I told you that there are three big isotope phenomena that we use. It's the altitude effect, it's a continental effect, and it's a seasonal effect. The seasonal effect is that every winter you have depleted rainfall, every summer you have enriched rainfall. It's going like this. Now, an obvious method is to sample, let's say, every 2 weeks, to sample a borehole every 2 weeks and to observe whether you see a variation that corresponds to your rainfall, precipitation, sinus curve. Now, if the water would be very, very young, actually just a couple of days old, your borehole would show these variations. It will actually reflect the seasonal variation. If it gets older, two things happen. First of all, there will be a shift. So you shift the isotope signal. So you can, if the groundwater is 3 months, 6 months old, you can directly read the shift in the sinus curve from your observations. So this works quite nicely. It works in mountain areas and it works in areas where you have a highly active system, highly permeable systems. But the second thing happens. The amplitude of the fluctuations will become smaller. So here in the rainfall, we have an amplitude of -11 to -6. So the older the water gets, on a scale of 2 weeks to very few years, 1 to 2 years, the smaller the amplitude gets. And after more or less 2 years, the signal is flat. It will not change anymore. So groundwater that is older than 2 years almost doesn't have isotopic variation anymore. Yes?
What's the precision, the errors of these measurements?
The question was, what is the precision? What are the errors of this method? Very good question. Now, the error of an individual measurement is more or less plus minus 0.1 per mil for O18 and plus minus 1 per mil for deuterium. Now, this means that you cannot detect fluctuations that are below that value or even within a standard deviation of these values. So within these variations, you cannot actually say with certainty whether there is any fluctuation or whether this is just probability. So this means that practically below 1.5 years, you cannot determine, more than 1.5 years, you cannot determine the age. And I would say when you fit a sinus curve, the precision would be plus or minus a month, with like for young waters with weeks to 1.5 years. So, but it gets, the precision is lower the older the water gets, towards 1.5 years. Yeah, so when it's very young, it's very sharp, and when it gets a bit older, it's less and less and less precise. And after 1.5 years, you can just say there's no direct impact. But this is very practical because you can always check. You don't have to detect the full sine curve. Also, outliers are interesting. So it's very interesting to just sample in spring and in winter and compare and see is there a difference. If there's no difference, you know the water is older than 1.5 years. Or you just check whether there are single outliers. This shows that there is a mixing with a young component. Now, there's also an equation attached to this that is shown in the upper right. The residence time T can be calculated based on the square root of the amplitude of precipitation divided by the amplitude observed in the flow squared minus 1 divided by the omega, which is the Kreisfrequenz, is the circular frequency value. So with this formula, you can actually calculate the age. And now if you want to know the error or certainty of this approach, you would actually add errors to A precipitation, to A flow, and omega is sharply defined. So the errors in the precipitation and the flow measurement determine how precise this method is if you do this based on the formula. So this is for very young water. Yes?
Was two questions about this chart. First, what is the adequate sampling frequency
Yes.
for recording these nice sine waves? And second, I wonder if, second question, I wonder if the phase shift in the sine waves can tell us something about hydrogeological processes as well as the amplitude reduction.
I will show you two methods. One is, the first one, this one is based just on, there were two questions for the online audience. So the first question was how the phase shift can be used. And the first one was sampling frequency, and the second one was use of the phase shift. So sampling frequency, as I said, every 2 weeks is a good recommendation. If you want or need to save money every month, is still okay. If you do research, you can also sample every week or more often. But a good recommendation is every 2 weeks. And if you want to actually reduce the effort, maybe you sample every 2 weeks. This depends a little bit on your logistics, whether you have someone in place who can do this. If you don't have it, you can put an instrument that collects water samples, or you can ask a local. But you could then measure just every month. And then if you see that there is variation, you could actually refill with, you sample every 2 weeks, but you measure every month. And then if you see there is an interesting area, you actually refill and you measure the samples in the second batch. Yeah? So this was the frequency. I did this for a company for a while, and we had to always save money for our customers. So usually these projects were done with 6 to 12 samples, not more. Yeah, so, but if you do research, you can actually invest more. Second thing was the phase shift. There are two methods. The first one is just based on amplitude. The second one is based on phase shift. And I will just show this now. Before I do that, this was just an ideal just an ideal graph, and this is a real graph. And this shows also related to errors that this is not that evident. You see that we have a sine curve, but single events can deviate from this sine curve quite significantly. So the real values that you see here are shown. However, the value below also shows something very interesting. The upper value is isotopes in precipitation. The lower value is isotopes in the spring. And this was a very important study for us because it was it showed evidence of a drought leading to no recharge during an entire year. So we actually saw in this graph that an entire winter was missing in our recharge value. So we lost it. There was no recharge. If there's no recharge, there's no negative input. And this was an evidence that recharge actually didn't take place during this single year. Now, the second method is based on the phase shift. And here you see data that are very interesting. They are taken at different depth in the unsaturated zone. So you have sampled at 0.5 meter, 2 meters, 6 meters, and 9 meters depth. And you see the isotope signal in these different depths. And you see that at the surface it's very pronounced. And then the deeper you get, the lower the variability is. In 9 meters it's gone. Yeah? And at the same time, you get an idea of the phase shift, which is very small. So you see that you have a very, very rapid recharge mechanism in this site. It's not a surprise, it's gravel, and you will probably observe the same thing in karst systems. But the formula that you see here is interesting because it refers to the phase shift itself. So the recharge is basically defined by the change in moisture with depth divided by the time to peak. And the time to peak corresponds to the phase shift. So this method actually uses the phase shift directly to say how fast the water moves. Yeah? So you actually observe how much delayed the peak is compared to an event that you know. And this is the time to peak. And you divide the water that has moved within that time, that is contained in the aquifer on the soil, divided by that time to peak or by the phase shift. And this is volume per time. This corresponds to recharge or flow. So this is the second method. This method works for ages of a year to more or less 30 to 50 years. If you can identify events and pinpoint them. Before we use tritium peaks from atomic bomb test, but this is gone. This doesn't work anymore. Now, if we have any event that we can actually identify in the past, we can actually use these events and then measure the moisture of flow of water volume contained in the column since that event and use the time since the event as the phase shift. So this is the second method.
Can I ask something?
Yes.
You mentioned that when we sample, for example, winter and then summer, and there is not much difference, the age of the water is...
Yes. The question is what happens if we don't have a difference between winter and summer? And then the sad answer is we cannot do anything. We cannot do anything. So if we do not have a difference between winter and summer, isotopic composition, the method doesn't work. So this...
But you said that we may have a very pure water or water. What I didn't understand.
Yes. I didn't understand acoustically.
When there is no difference, that means that the water is very old.
Okay. So the question was, if there is no difference, does it mean the water is very old? If there is no difference in the isotopic variation, it means that it has been smoothed out completely by dispersion processes. So if the original signal has disappeared, this means that the water has traveled enough time to actually eliminate all the differences by dispersion. And this happens after 2 years. After 2 years, the original input is gone. The second thing was, if you do not have any difference in your isotopic input, this method doesn't work. So if the rainfall is always the same, for example, you imagine a tropical situation in the Amazon and it's every day the same rainfall pattern, then this doesn't work because you don't have isotopic differences that you can use. Then you have to look for something else. So I just show you several methods. You have to put them together that range from very short to older. We come to other methods that would work in that context too. But the easiest one is to use the isotopic differences and to check, do I see them? And when you do not see them at all, you know that your groundwater, and if you have them in the rainfall but do not have them in your spring, then this is a sign that your groundwater is older than 1.5 to 2 years. Because usually after 1.5 or 2 years, in a sedimentary porous aquifer, these differences disappear by dispersion completely.
So the only correlation between isotopic differences and the age reaches only 2 years, we cannot make a
No, older, then you have to use one of the methods that I will show now. Then you have to go. But there are some cases in which you can make a residence time estimation that is far longer, and I just want to show you this one nice example, but this is, you need to be very lucky. This is an example from Switzerland where isotopes, stable isotopes of water have been used to make a residence time estimation of 1 million years of magnitude. And this was because people were very smart. We had one aquifer above, which was sandy, and an aquifer below, which was clay. And people knew from the paleo water study that there was a change in the rainfall between 1 million years ago and now, Pleistocene. And it was known more or less what the difference in stable isotopes was. And this study shows how the change in the upper aquifer affected the lower clay aquifer. So you can see here how the signal has moved into the clay aquifer. This is a study that was done for atomic waste deposit, and what these people wanted to know was the speed by which the new signal travels into the clay. But this is context. So if you have a situation where this context is given, it works. So sometimes if you have a clay aquifer, you keep a signal of the isotopic change of the recharge water above, and you can actually track this if you look at the composition of the clay. I just wanted to show this. This is a kind of circus experiment, very rare. But understanding changes in isotopic signals, also between like at paleo scales, going far into the past, can in some cases work. This is another study that we did where we actually analyzed this in a deep clay profile. So clay profiles can be very interesting. It was a saline clay, and we actually studied the isotopic composition in the clay below an evaporation pond. And again, we were looking here for isotope changes in the clay. So clays can actually be archives of isotope signals and be quite interesting, especially if you have environmental changes. So this is an application where we, this is from Portugal, where we studied salt and isotope signals in soils. We have different sites, Mitra, Alvito, Ric, and Mura, with different climates, the soil profiles that have different degrees of salinity. And again, here we studied how the signal of different seasons have traveled into these profiles. And basically what we do is we try to track the depth that a certain seasonal signal has traveled into the soil. You see this here clearly as the peak. This is then winter, summer, winter, summer. And we accumulate the moisture above the peak according to this formula. This is the integral of the moisture down to a certain depth at which we know the peak is, and we divide by the time to the peak, the time that has passed since the peak. So here we actually accumulate the moisture above that peak. We know how old it is, and we divide the moisture by the time to peak, and this gives us then the flow. Now, these are all methods so far that are built directly on stable isotopes of water. They can be extended sometimes into like longer residence times, but usually they are just for quite young water. Now the next category of age dating residence time analysis is based on the tritium input method. And in the past, we could use the tritium peak from the 1960s. You still see it here. This is the mess that we have created with atomic bomb tests. And this is like the deviation from the normal radioactivity that we had. And you see that it peaked in 1963 more or less, and then it went down. And we could actually monitor this. But this peak is gone. It's actually washed out of our hydrological systems. So we cannot use this anymore. However, tritium is still a useful tracer, because tritium still has, based on natural background radioactivity that is created by cosmogenic rays, still has a radioactivity of 5 tritium units. A tritium unit is a certain amount, very low amount of radioactivity, and the natural radioactivity of water is 5 tritium units. Now, tritium decays within a half-time of 12.3 years. Every 12.3 years, the radioactivity decays by a factor, is half. Yeah? So it's reduced by a factor of 2. This means if we start with 5 tritium units, then after 12 years, we still have 2.5. After 25 years or 24.6 years, we still have 1.25. After 37 years, 37.1, we still have 0.675. And we can measure down to 0.1, 0.2. So you see that after about 50 years, we have 0.3 something. And then after 62 years, we are close to the detection limit. So if we take the natural input of tritium to a system, being more or less 5.5, you get the real input from the International Atomic Energy Agency, IAEA, by registering and downloading the data for your country. So you know what the input was, and then you measure the real activity that you've got in your system, and you can simply calculate the activity that you the age using this equation that we will also use for C14 in a minute. So this is the current activity that you measure now. This is the initial activity, A0, that you get from the IAEA. You know that there is an exponential decay, that is true. Everywhere in the universe, anytime, doesn't change, it's like an eternal thing. This is the time, and this is the decay constant. We know that the ratio of activities in the beginning and today can be used using the decay constant that is published to calculate the time, just by solving this equation properly. Now this is the way we actually can determine ages of up to 67 years using tritium. This still works today, and this will work in the future. There is even another method that is nice that I have just added here. The tritium that has decayed in the past has been converted to helium. So when you have tritium that decays, it creates helium-3. And the tritiogenic helium is still there, although the tritium is gone. So until today, we can still look for traces of past tritium in our groundwater systems and use this to improve the age estimation. So this is indicated by these, and then you can even use the amount of helium that was produced from tritium and use this to estimate the residence. So this is a method that works from, let's say, 5 years to 67 years. Yeah? So now we can cover everything from weeks to 2. We have a little hole between 2 and 5, and we can cover the range from 5 to 67. Yeah? In the beginning, I told you that we also have pollution traces, that our atmosphere is polluted with many gases that have been produced for industrial purposes. Here you see the concentration of the anthropogenic sources in the atmosphere. This is the tritium peak once again. But then you know all that we have produced CFCs, chlorinated fluorocarbons, different types that are forbidden since 1992 or 3 with the Montreal Convention. And I have already mentioned SF6, which is an industrial gas that is not forbidden. It's still being produced. It's too useful, too needed, in the Montreal Convention, we did not exclude the production of SF6. So CFCs 11, 12, and 113 were actually cancelled, and SF6 still grows. You see the input function of CFCs. So I have used CFC age dating myself very successfully in several cases, but this is actually phased out. So you basically use the concentration of CFCs, you measure them, and you can use them to estimate the age. And this works for ages between, let's say, 5 to 150 years with some modeling tricks. So this is the range that you can cover. But this is actually a dinosaur, so I will move directly towards SF6 data because CFCs are gone. So SF6 is quite simple. You need the input function of SF6 in the atmosphere. This is available, it is measured and documented. You can download this from University of Berkeley, who has this, and several environmental agencies who collect these data. They are actually updated every year. And we know how much of SF6 is available in the atmosphere. The only thing that you need to calculate is how much SF6 can be dissolved in water. Because we just know the concentration in the atmosphere of the gas, but not the concentration in freshly recharged groundwater. Now when we use SF6, there is no radioactive decay. SF6 does not decay, it's stable. And it will usually not disappear because in water it's very well isolated and packed. We just need to make sure that we take the sample without the gas. So what we need to do is basically, we'll do an exercise for this afternoon. We need to calculate from the known SF6 concentration in the atmosphere the corresponding SF6 concentration in water that we had in 1940, 1950, 1960, 1970 until today. This is easy. It's controlled by the Henry equation that just depends on temperature. And we need to correct for the decrease of pressure with altitude. So basically, we need to know the temperature at the recharge location because it controls how much SF6 we dissolve in water. And we need to know the elevation of the recharge location because it controls how much the pressure of the atmosphere and therefore also the partial pressure of SF6 has decreased. Now we can determine the elevation of recharge with stable isotopes. Yeah? So there the circle closes. Now what we do then is we first calculate how much the pressure is lower at a certain altitude using the international barometric formula. Then we have a lower pressure, and we assume that the SF6 concentration will also decrease in the same manner because it's partial pressure. Now with that pressure and the temperature at the recharge location that we got from stable isotopes, or that we know, we calculate how much is dissolved in water. And now we make a curve that shows the input function in the water for all the years that are possible. This starts, SF6 production started in the 1940s, end of the 1930s, 1940s. And now it's very easy. We just need the measured concentrations, and I'm not on the camera anymore, I'm there. So we just take the measured concentration and we determine the intersection with the curve. We go down and we have the age of the recharge. We have the recharge. So it's actually quite simple. So this works for groundwater ages of, up to 80 years, basically. If it's older than 80 years, there's no SF6. and if it's recent, then we have the full concentration. Sometimes, very rarely, there are deviations. So in Italy, in Cyprus, Greece, Turkey, Tunisia, Algeria, we could use the functions as they are. But I did one study in Switzerland, and in Switzerland you have actually production of SF6. You have companies that produce SF6, and they have leaks. So if you are close to an SF6 factory, then you have to make a correction. And in this case, we have two. Yeah? But for most of the world, where you don't have SF6 producing companies, this is not a problem because the atmosphere actually mixes everything quite well. Okay, now we have just 2 methods left. I think I can, and I should, like close at 1 o'clock, so 5 minutes. We can do this also for other gases and combination of gases. Another one is krypton-85. Often I use SF6 instead of krypton-85 and tritium. I just want to mention the krypton-85 here. Krypton-85 is the gas that is released by factories in which rods of atomic reactors are open for recycling. So when you have an atomic reactor and you actually recycle it, you cut it open, and during the process, krypton-85 is released. And it will, because it's a noble gas, emanate from the factory. You cannot keep it even through thick walls of concrete. So it actually emanates, and the concentration of krypton-85 increases worldwide since many years, inevitably. Unfortunately, as long as we have atomic reactors and as long as we cycle rods from atomic reactors. So this has a similar input function to SF6, it's just going up. The difference with krypton-85, it has radioactive decay. But this gives us a possibility to actually determine, and I just want to highlight this, something new from the combination of 2 age dating methods. Here we have combined tritium on the x-axis and krypton-85 on the y-axis. We could also use SF6. Now we construct a line on the right-hand side that corresponds to both values combined. We take the tritium value of a certain year or age and the corresponding krypton or SF6 value. And both give a line. And this line corresponds to ages from 1 to 30 years that are determined by both traces coinciding. Is that clear so far? There is, this thing has already bitten me twice. This is my own blood. Nasty. Can they beat twice? Then, or otherwise there are 2. So, now we justify something that's interesting for salinization studies. We assume that there is a second water source that is very old, a paleo water, a salty water. And we construct mixing lines from that young age to the old water and from the old age to the water. And we call this, a Segel, sail. So we call this shape, sail, what you have in sailing boats. Yeah? Now this gives us 2 pieces of information. The first one is the age. So these are the ages. This is very young and this is old. And it gives us the mixing ratio between the young water and the old compound. Yeah? So you can see I have young water of a certain age mixing with 70% of old water. Yes, and the last one, now we have covered actually ages, we can cover ages up to more or less 100 years. And the last method that I want to show is the carbon-14 age dating. And this will now start with 1,000 years and go up to 500,000 years and go up to 40,000 years. Again, here, we take the activity of carbon-14 in rainfall. There is a permanent input of radioactive carbon to our atmosphere, to our biosphere, to our body, to our rain. In the CO2 that is in this room has a radioactivity that will give a value of 100 for modern radioactivity. So we just give it a radioactivity of 100. % modern carbon. And this is the input value, 100. And then we have the same equation that we have for tritium, exponential equation with a decay factor. The decay of C14 takes 5,730 years. This is the time that has elapsed. And this is the value that we measure, that we observe. Now, if the groundwater is very young, it's 100. And if it's more than 40,000 years old, you cannot detect it anymore. It has decayed. Yeah? Because we have 100, after 5,730 years, we have 50. After 11,460 years, we have 25, and so on, until the detection limit. And then it's basically groundwater that is older than 40,000 years cannot be detected anymore. And then we know it's very, very old. Then we have other methods. Now, in the case of C14, we must add something. Because C14, unfortunately, especially in the Mediterranean, is diluted by dissolution of carbonate. And this introduces a major error. Now, there are several correction methods. A very, very simple one, very often used, is the one by Vogel. And he says you just multiply the whole thing with 0.65 to 0.75. I'm done in a minute. Forecast. 0.75 to 0.9 for sediment with fine-grained carbonate, and 0.9 to 1 for crystalline rock. This is a rough method, but it's very often used. I don't like this method very much because it introduces major errors. So there are better methods by using the C13 information that we have. We can measure the stable isotopic composition of the stable isotope of carbon. And if we dissolve carbonate, we will also increase the C13 value will become very similar to the carbonate rock. So we actually do a mixing calculation between the C13 that we have in the water, the C13 that we have in the carbonate, divided by the difference between those. And this shows us how much carbonate we have dissolved. And this gives us a new correction factor that we can plug in here. And there is even a third method that I prefer. This is based on chemistry. If we have dissolution of carbonate, it will affect our chemistry. And with this formula, we can basically calculate a new correction factor or a mass of a new correction factor based on the mass of DIC from recharge to final. And this can be calculated from the chemistry. So we actually calculate the mass of chemicals that have been added to water from the solution of carbonate. And once we know it, we can calculate the chemical mass balance correction factor that we plug in here. So these are the methods for residence time analysis. And this was the material that I wanted to present. I still have the compartment modeling open, but this is something that I will just do in the exercises afternoon because it's more practical. This is for the afternoon and the outlook. So what I wanted to show you today was how we can move from just the pure interpretation or the qualitative detection, I have evaporation or not, a bit further into quantitative isotope hydrology. So I try to convey how you calculate the calibration fractionation, how you calculate diffusion fractionation, Rayleigh fractionation. In the context of groundwater salinization, it helps us to better distinguish the salinization processes. So instead of just having seawater intrusion, we can now, using these tools, see is evaporation significant, is evaporation correlated with salinization, what is the source of recharge, at which altitude do we have it, what is the age, do we have paleo waters that play an important role, do we see this in the age dating, And do we have input of nutrients or other substances in a closed basin context that actually cause our increased salinity? Thank you very much for your attention and nice to meet you.